Welcome to the Network Plus Prepcast, your dedicated audio companion for mastering every objective on the CompTIA Network Plus certification exam. This series is produced by baremetalcyber.com. MAC Tables and Forwarding Decisions examines one of the most fundamental technologies in networking. Layer 2 switches operate at the data link layer of the OSI model and are responsible for making frame-based forwarding decisions. Their purpose is to move traffic efficiently within a local area network without requiring IP routing. These switches use hardware-based logic to direct Ethernet frames from one device to another by analyzing source and destination MAC addresses, creating the basis for local connectivity and communication in almost every network design. Understanding MAC-based forwarding is crucial for any network technician. It allows switches to intelligently direct traffic instead of sending it to every port like a hub would. This makes network communication more efficient, reducing unnecessary congestion and isolating traffic between devices. MAC addresses serve as the unique hardware identifiers for each device, enabling the switch to associate each one with a specific port. When implemented properly, this leads to faster communication, more secure traffic paths, and reduced overhead within the LAN environment. Layer 2 switching fundamentals begin with the understanding that switches process traffic at the data link layer using MAC addresses rather than IP addresses. This means they handle Ethernet frames, not packets. They analyze the destination MAC address in each incoming frame and determine the correct port to forward it to. Switches cannot route traffic between IP subnets or interpret Layer 3 headers. Their role is entirely focused on local communication between devices on the same broadcast domain, making them critical to campus and branch network designs. The MAC address table, also called the Content Addressable Memory Table, is the core of a switch's decision-making process. This table contains a list of learned MAC addresses and associates each one with a specific switch port. When a frame arrives, the switch consults this table to determine where to forward it. The MAC table also includes an aging timer to remove entries that haven't been used recently, helping keep the table accurate and preventing outdated paths from interfering with traffic flow. Switches learn MAC addresses dynamically by inspecting the source address of incoming frames. When a device sends a frame, the switch records the source MAC and the port it came from. If that address is not already in the table, it gets added. If it is, the switch updates the timestamp to reflect recent use. For destinations not yet in the table, the switch floods the frame out of all ports except the one it arrived on. Once the destination responds, the switch adds it to the table and stops flooding subsequent traffic. The behavior of forwarding versus flooding determines how a switch handles known and unknown destinations. When the destination MAC address is found in the table, the switch forwards the frame only to the correct port. When it's unknown, the switch floods the frame to all other ports. This process continues until the switch learns where the destination is located. Efficient networks aim to reduce flooding by ensuring MAC tables are populated quickly and accurately, which helps minimize unnecessary traffic on the network. Frame filtering and loop risks are major considerations in Layer 2 environments. Switches can be configured to filter specific MAC addresses or protocols at the port level. However, when physical loops exist between switches, like redundant paths without proper control mechanisms, broadcast storms can occur. These storms result from frames circulating indefinitely, consuming bandwidth and overloading devices. To prevent this, switches use loop prevention protocols, which we'll cover later, but implementation awareness begins at the port configuration level. Switches eliminate collision domains by assigning each port its own domain. This is a key distinction from hubs where all connected devices share the same collision domain, leading to frequent retransmissions. With switches, collisions are avoided because each port operates independently, often in full duplex mode. This enables simultaneous sending and receiving of data, improving performance and reliability. As a result, switches create much more scalable and efficient LANs than legacy hub-based systems. When a switch boots up, its MAC address table is initially empty. As traffic begins to flow, The switch rapidly populates the table by observing the source addresses of incoming frames. Within a few seconds of activity, the switch learns where each device resides. Over time, the table stabilizes, and the switch becomes highly efficient at forwarding frames to the correct destination. This initial learning phase is important to consider when bringing devices online or rebooting network equipment. Switch ports go through several states to manage traffic handling. These include listening, learning, and forwarding. In the listening state, the switch waits for topology information. In the learning state, it begins to populate the MAC table by examining source addresses. Once forwarding is enabled, the port actively transmits and receives traffic. Temporary states like blocking or discarding are used in loop prevention protocols to suppress traffic and avoid duplication. Understanding port states helps explain how switches stabilize during network change. The size of the MAC address table can impact switch performance. Most switches have a limit on the number of entries they can store. When this limit is reached, new entries may replace older ones, or be dropped altogether, depending on the aging policy. If a table overflows, the switch may revert to flooding behavior, increasing unnecessary traffic. Large networks must account for MAC table capacity when selecting switch models to avoid performance degradation due to overflow or excessive aging. For more cyber content and books, please check out cyberauthor.me. Also, there are other podcasts on cybersecurity and more at baremetalcyber.com. Frame encapsulation and decapsulation are key functions performed at Layer 2. When a device prepares data for transmission, it encapsulates the payload in an Ethernet frame, which includes a header containing the source and destination MAC addresses. This frame is then transmitted across the network. At each hop, the Layer 2 device reads the header, determines the next destination, and forwards the frame accordingly. When the frame reaches its destination, the receiving device decapsulates the frame to extract the payload and pass it to higher layers for further processing. Address Resolution Protocol, or ARP, plays a critical role in enabling Layer 2 forwarding decisions when devices only know an IP address. ARP maps IP addresses to their corresponding MAC addresses by sending a broadcast request asking who has this IP address. The correct device responds with its MAC address, which is then used for frame delivery. This MAC address is stored in the ARP cache for future use. While ARP operates at Layer 3 conceptually, its results are essential for Layer 2 switching behavior. Switches handle unicast, broadcast, and multicast frames differently. A unicast frame is directed to a single destination and is forwarded only to the port listed in the MAC address table. Broadcast frames are sent to all ports except the one they arrived on and are used for functions like ARP requests. Multicast frames are intended for multiple recipients but not everyone on the network, which may treat multicast traffic like broadcast unless specific multicast handling protocols are configured. Filtering rules can help reduce the load from broadcast and multicast traffic on the switch. Network segmentation using switches enhances security and performance. Each switch port acts as a boundary that isolates traffic to its destination. By segmenting users or devices into different VLANs, administrators can reduce broadcast domains and control access to sensitive areas of the network. Switches enforce these boundaries and keep traffic flows separate unless routing or trunking is explicitly configured to bridge the segments. Segmentation is a vital tool in managing traffic load, improving performance, and enhancing network security posture. Frame forwarding timelines are optimized through hardware acceleration features in modern switches. When a switch receives a frame, it uses hardware-based lookup tables to determine the correct output port almost instantly. This high-speed decision-making enables low-latency communication between devices. Delay is typically measured in microseconds, but performance may vary depending on switch model, table size, and current load. Efficient forwarding timelines are critical in environments where speed and responsiveness are essential, such as voice-over IP or high-frequency trading networks. Layer 2 switches have limitations that affect how they are used in larger networks. They cannot make routing decisions, so they cannot forward packets between different IP subnets. They also maintain a single broadcast domain unless VLANs are configured to segment traffic. As networks grow, Layer 2 devices may face challenges with scalability, including MAC table overflow and broadcast traffic buildup. To overcome these limitations, Layer 3 switches or routers are introduced to provide IP-based routing and control traffic across broader domains. Loop prevention is a major consideration in Layer 2 networks because loops can lead to broadcast storms and traffic duplication. The Spanning Tree Protocol, or STP, is used to detect redundant paths and block one or more ports to prevent loops. If the active path fails, STP can re-enable a blocked path to maintain connectivity. This dynamic adjustment ensures that the network remains loop-free and stable while still offering redundancy. Understanding how STP works and how to identify loop issues is essential for troubleshooting and implementation. Layer 2 switches serve as the foundation of local area networking by efficiently handling traffic between devices using MAC address tables. Their ability to learn, forward, and isolate frames ensures that traffic is directed accurately and with minimal delay. They do not route traffic or interpret Layer 3 headers, but their role in managing local communication cannot be overstated. Whether segmenting a network, reducing collisions, or enabling low-latency transfers, Layer 2 switches are critical infrastructure components in every environment. The key takeaways about Layer 2 switches include their MAC-based forwarding behavior, their reliance on address tables for decision-making, and their role in managing unicast, broadcast, and multicast traffic. Switches enhance performance through hardware-based decisions and contribute to security and segmentation through port-level isolation and VLANs. Understanding how they encapsulate, decapsulate, and forward frames, along with how they prevent loops and manage traffic types, is essential knowledge for the Network Plus exam and for effective network design and support. Thank you for listening to this episode of the Network Plus Prepcast, your trusted audio guide to the CompTIA Network Plus certification. This episode was produced by baremetalcyber.com. For more cybersecurity podcasts, books, and resources, visit baremetalcyber.com. Thanks for joining us for this episode of the Bare Metal Cyber Security Plus podcast. For more episodes, tools, and study support, visit us at baremetalcyber.com. And before you take the test, make sure to check out the practice questions in the book Achieve CompTIA Security Plus SY0-701 Exam Success by Dr. Jason Edwards. They cover every domain and are a powerful way to lock in your knowledge.